Hash tables are a very useful data structure, and today I'll explain the theory behind hash tables, and then we'll go on to implement a hash table in C. So, in one of my previous videos, I explained the concept of a dictionary. So a dictionary is a list of key value pairs, right? So each key is associated with a value, and each key is also unique. Now, let's say I created a dictionary which has, for example, my name, which is Ali, my surname, Awan, my hobbies like programming, age, and many more. Now, something interesting you might notice is that as we increase the number of key value pairs in the dictionary, the time it does to do operations on them will also increase linearly. What do I mean by that? Let's say the number of elements we have in the dictionary can be represented as n, which is the number of key value pairs. As n increases, the time it takes for me to find, for example, a value associated with a key will increase linearly. So let's take an example of the key age. Right now, it will take me 4 iterations to be able to find the key age if I'm looping over all of the keys. Let's say there are 100 elements. Then it will take me 100, and age at the end is the last key value pair. Then it will take me 100 iterations to find the key. So what this means is we have a linear time complexity, also known as O of n. Now, normally this isn't a bad thing, but if we are wanting a data structure which is similar to a dictionary in the sense that we have key value pairs, but is much faster to be able to index keys, add keys to dictionary, and also remove them, well then what alternative do we have then? That's where the idea of a hash table comes in. So let's go back to this example right here. I've got a key value pair with key name and the value being Ali. Let's ignore the value for now and just look at the key name. So I'll create a table right here, and it will have multiple elements. So it will have 5 elements, and we have the indexes on the left. How would a hash table work in this case? Well, a hash table works by getting a key and creating a hash using something called a hash function. Now, what the hash function does and how we can find a good hash function is out of scope of this video because it's quite a complex topic. However, what we need to know is that a hash function will take a key and it will apply some algorithm to it to generate a hash, which is usually a large number. This large number is going to be unique to the key, so that means that if I pass a key into a hash function multiple times, I should get the same hash from it. It shouldn't change. And ideally, every key should have a unique hash associated with it, which is what creates a good hashing function. Now, once we've hashed our key, and we've got the hash from it, what does this hash do? What does it mean? Well, we can use this hash to find a position to store this key value pair in a hash table. How do we do that? Well, then we use the modulus operation. So here I've got a table which has 5 elements, and so I can use modulus 5 on this hash to get a index for it. So in this case, 2570 modulus 5 will give us 0. So I can store the key value pair name Ali at position 0, right? So as you can see, that's the process of adding elements to a hash map or hash table. Let's take a few other examples. So we have my surname, hobbies, age. These are the other keys I showed you guys before. How would I approach adding these to the hash table? Well, let's hash surname, and we get a hash of 3266. I find the modulus of, I apply the modulus 5 of it, and I get a value of 1. So surname will go to index 1, and so will its key. Let's do the same for hobbies. So then I hash hobbies and I get a hash value of 1049. And I run the modulus on it, and I run modulus 5 on it, and then I get an index of 4, right? So I put hobbies at index 4. So we also put the key there. Now let's do age. Let's say we hash age and we get 9425 as the hash. I run modulus 5 on it, then I get a hash value of 0. Now what does this mean? I store age at position 0, but name is already there. So what's happening here? Well, what we just saw is something called a collision. And a collision is something that occurs when two or more keys end up being stored in the same position. So here we're trying to store age and name in the same position. So how can we solve this problem of collisions? Well, I'm not going to explain it right now because there are multiple techniques we can use to solve collisions. I'll explain in the next video. However, for now, we'll just ignore collisions and we'll just not add the key to the hash table, which isn't practical, but it will serve for us to understand how the data structure works. So now that we have an idea of how hash tables work, I want to go back to the point I brought up at the start of the video, which is time complexity. You might have noticed is that adding elements into the hash table is very simple. It's one operation. We just hash the key and we just run modulus on it to find the index. So removing values from the hash table is also very fast. We just get the key, hash it again, find its index, check if the index exists or value exists at the index, and we just remove it. So what this means is that we have a time complexity of O of 1, which means the hash table's operations of adding, removing, checking elements is constant, no matter how big the hash table gets. So if I've got a hash table which has 1,000 elements, or I've got a hash table which has 10 elements, the time to do all these operations will be relatively the same. And that's very powerful because a time complexity of O of 1, or constant time, is much faster than O of n, or linear time. And this makes it very useful for practical applications where we need to have high performance and a lot of reliability. So now I'll implement a hash table in C. Okay, so here I have a very simple hello world program, and I'll start writing up a hash table right here. So the first thing we need is a structure to hold the hash table. So we can do that through a typedef or create a hash map or hash table data structure. And this will have 3 members, or have an array of strings we call keys, another array of strings we call values, and an integer called count. Count just tells us the maximum number of elements the hash table can hold, which is also the size of these arrays of keys and values, right? I'm also going to create a function to initialize the hash table with values. So let's say I'll call it void hash table initialize. This will just take in a hash table. It will take in the number of the count, which is the number of elements we're going to have in it, and then we'll just allocate memory for all of these variables in the hash table. So I'll use the struct initialization syntax, which was introduced in C11, I think, or not C11, C99. So what we can do is I'll just set keys to be equal to, we'll allocate memory for it. So I'll say size of a child pointer times by the number of strings we're going to have, so the number of keys and values, which is equal to the count, right? I'll do the same for values, and then I'll just set count equal to the count the user provided. And these should not be colons or semicolons, they should be commas. Now, we've allocated memory for the keys and values, or the arrays of keys and values. I want to also initialize them to 0. That's quite useful because by default, malloc doesn't initialize the memory it gives back to us. It just contains whatever values were there before. So by initializing them to 0, we can prevent some memory bugs, and also we can do something useful, which is check if a specific key is empty based upon if it's null, because if a piece of memory is null, it's going to have a value of 0 to it, so it has not been initialized to anything, or rather it does not contain any value. So I'm just going to do that here. I'll do a memset of hash table at keys. I'll set them all to 0, and then we'll just do this right here. So I'll just paste that, and I'll do the same for the values, right? And that's it. That's how we're going to initialize it. It's pretty simple. So I'll just create a hash table right here. We'll initialize it with hash table initialize. I'll pass in the pointer to the hash table. I'll give it a count. I'll say, let's say we do 20 elements for now. let's compile it. Hope it works. Okay, it does compile. Yeah, seems to be doing good. So now we have 3 more functions we have to do. We have to implement. The first is adding elements to the hash table. Second is getting a value associated with a key in the hash table. And the third is removing elements from the hash table if they exist. So how can we do that? The first one, which is adding elements to the hash table, we can implement that pretty simply. So I'll create a function called hash table add, which returns a boolean. Now the boolean is going to tell us whether we were able to add the key value pair to the hash table successfully, because maybe there's no space left in the hash table, so we can't add it, or the user might have given us a duplicate key, which is not allowed, so we won't be able to add that to the hash table. So I'll pass in a char pointer, which is the key, and another char pointer, which is the value we're going to add associated with the key. What I'm going to first do is check if there is space in the hash table. So if hash table, actually we have to first generate a hash for the hash table. So what we can do is we can use a gen hash function to generate the hash for it. Almost forgot to do that. Now I'm going to be using a hash function pre-made for us because it's kind of complex to create a good hash function. It's kind of out of scope of the video. So this is the hash function we're going to use. It's called dbj2. I'll leave a link to it in the description below. You guys can just copy it off there. And I'm just going to paste it right here. So let's just format it. So it's going to be unsigned long. I'll call it gen hash. Right. Just remove the comment right here. So what we can do is we can get the index by hashing the string or the key, then using the modulus of the number of elements in the hash table, which is going to be hash table account, and this will give us an index. We can now check if an element already exists at the index. So let's see. So if hash table at keys at index is not equal to null, right? That means we've already got something there. There's already a key value pair there. So that means we can just return false, because in this case there's a collision. Just say collision, and then I'll just say key exists at index, and then just pass in there. So I'll just say index here, and then the key is going to be this right here. If there is no key stored at that location, then it's free, so we can store our key value pair right here. So I'll just do hash table of keys at index is equal to str duplicate of key. Now what str duplicate does, I'll do the same for the value as well. Str duplicate takes in a key, and then it allocates memory on the heap for a copy of the key. It copies the data or the string into that piece of memory, and then no terminates it. So we essentially just get a heap allocated copy of the key, which is very nice. So then we can just put it there, then we just return true. So let's see if we can add some elements to this dictionary. So I'll say hash table add, pass in our hash table, a key of, let's say, name Ali, printf success, adding key print out success right here. I'll do this a couple times. Okay, we got an error. Should have 2. What's there? Okay, we've got the two keys in there. Right, so we've been able to add key value pairs to the hash table. The next thing is getting a key associated, so getting a value associated with a key. We can do that through child pointer, let's say, return the value, hash table get value at key. Kind of a long name, but it's quite descriptive. We get a hash table in here, we pass in a key that we want to find the value of. So what we do is, you once again just use the hashing function to get an index. So we'll just hash the key and then modulus the number of elements the hash table can have, which is hash table account. We'll just check if an element exists at this index. So first off, if there is no element at key, so it's equal to null, I'll just return null right here, which means actually we can do, instead of doing this, we'll just do this. It's not equal to null. We'll just return hash table keys index. And what this means is, if there is a value, a key at this index, we just return the value. I have to change that. We just return the value associated with the key. Otherwise, there is no memory there, so it's set to null. So we just return null as the value. So let's try running that. Value, let's say key is this, then value is this. We can do, I'll say key surname, and then I'll do hash table get value at key of, let's say, surname. Does that work? We got an error. I forgot to pass in the hash table. Compiled. Okay, we got the surname. Let's try to get an invalid key. So I'll say a bunch of random letters. We should expect to get here is null, because there should not be any key with a value that I've just typed down right here. So we should instead just return null from this function. So what I expect to see is null. Yeah, we got null. It seems to be working. The last function I want to add is a function to remove a key value pair in the hash table. We'll do that. I'll just return boolean if we succeeded or not. Hash table remove. This will take in a hash table. Also take in a key. We will once again just hash it to see if we can find an index. We will check if the index, if the key exists. Let's say, actually first we can check if there is no key at this index, which means that this key value pair does not exist in the dictionary. We just return false. Another case we can have is that we do find a key value pair. However, this key value pair is a collision, so we might have, let's say we've got keys name and Ali. I hashed name first, and this got stored at index 0. Then I hashed my surname, and that ended up being the same index. And we're trying to remove our surname. What would happen in this case is that we will end up removing the name key value pair, because surname stores somewhere else because of the collision. So what we can do is check using the stir compare function that this key is actually the key we are trying to remove. And we can do that by just comparing this key at the index with the key we provided, the user wants to remove. If that's not equal to 0, then these two keys are not the same, which means that we're going to end up removing the wrong key value pair because there's a collision with the hashes. So we just return false again. If none of these conditions are satisfied, then we indeed have found the key value pair at this index, so we can remove it. The way we do that is by just freeing the memory at this location. So say hash table keys of index. I'll set that to be equal to 0. Sorry, we'll just free that key at that index, and then we'll free the values. Then I'll just set that piece of memory to 0. So I'll say hash table keys at index. I'll just set that to 0. And this be a size of a Chart pointer. Let's see if this compiles. It did compile, so let's test it out. Let's say remove key hash table remove possible hash table, and I'll try to remove name. Actually, let's do surname. Let's try to remove surname first. Then we'll see if we can get it again. Compiled. Okay, so we seem to have removed the key value. So we removed the key surname, and we tried to retrieve it again. We got nothing here. What I was expecting to get was a null pointer. So I might have just messed this up a bit. Maybe I have to. Yeah, there we go. So the problem is, when we do this just returns a pointer to that key's position. What we actually want to do is just increment the key's pointer a certain number of the number of elements we need to get to the key we're trying to remove. So we just replace the brackets with a plus, and that fixes it. So let's compile, run it again. We get null there. Let's try removing a key which does not exist in the dictionary. So let's say random. We could not remove that key because it does not exist. So I want to show you guys what would happen if we try to, let's say we try to add in a bunch of elements right here. So let's say we do add 5 of them, and then I shrink the size of the dictionary down to 10. You'll see why I'm doing this. I'll just change the keys right here. So let's say AL, ALB, and just create a bunch of random keys. What should happen now, if this works, is, okay, we got collision right here. So key exists at index 2 ALB. What's happening here is, since the hash table is so small, we end up having hashes mapping to the same index multiple times, which causes collisions. And because of this, since the hash table is quite small, so there's higher likelihood that happening. When the hash table is very large, and we can have a larger modulus to apply to the hash, the chances of a collision are a lot smaller. But as the range of values we can have an index of decreases, the likelihood of a collision happening also increases. Now, in part, this can also be attributed to the hash function. A good hash function should ideally minimize the chance of a collision happening, but when we've got a small range like this, it's kind of inevitable that it's going to happen eventually. So we have multiple techniques that we can use to deal with collisions, and I will go over those in the next video. But for now, just know that this problem exists and there are multiple techniques we can use to solve it. So that's the end of the video. I hope you guys enjoyed it. If you have any comments or questions or suggestions you'd like for future videos, please leave it in the description. And I made a video previously about dictionaries, so if you didn't get the idea of key value pairs, I recommend you check that video out first. Thank you for watching. I'll see you guys next time. Bye.